National Electrical Code Section 310.15.6 addresses ampacity adjustment for dwelling unit services and feeders. This section allows for a specific ampacity calculation method under certain conditions when sizing service conductors and feeder conductors that supply the entire load of a dwelling unit. The key consideration is whether the structure qualifies as a dwelling unit. A dwelling unit, by definition in the National Electrical Code, is a single unit providing complete and independent living facilities for one or more persons, including permanent provisions for living, sleeping, cooking, and sanitation. When a mobile home is used strictly as a construction office, it typically does not meet the definition of a dwelling unit. The primary function shifts from residential living to a commercial or business operation. The presence of office equipment, computers, printers, and related infrastructure becomes the dominant load profile. Consequently, the ampacity adjustment provisions of Section 310.15.6 would generally not be applicable in this scenario. Instead, standard ampacity calculation methods outlined in Article 310 of the National Electrical Code should be followed. These methods require a more detailed assessment of the actual load served by the conductors. To accurately determine the conductor size, the total connected load of the construction office must be calculated. This includes lighting, receptacles, HVAC systems, and any other electrical equipment present. After calculating the total connected load, demand factors may be applied as permitted by Article 220 of the National Electrical Code. Demand factors allow for a reduction in the calculated load based on the understanding that not all connected loads will operate simultaneously at their maximum rated capacity. The specific demand factors applicable to a construction office can be found in Article 220, which provides guidelines for various types of occupancies. After applying the appropriate demand factors, the resulting value represents the minimum ampacity required for the conductors. The selected conductors must have an ampacity equal to or greater than this calculated value. Furthermore, it is essential to consider any applicable correction factors for ambient temperature and the number of current carrying conductors in a raceway or cable. These correction factors adjust the ampacity of the conductors based on the environmental conditions in which they are installed. High ambient temperatures can reduce the ampacity of conductors, while multiple current-carrying conductors in close proximity can lead to heat buildup and require further ampacity dating. The National Electrical Code provides tables and guidelines for applying these correction factors. In addition to ampacity considerations, the overcurrent protection for the conductors must be sized appropriately. Overcurrent protection devices, such as circuit breakers or fuses, protect the conductors from overload and short-circuit conditions. The overcurrent protection device should be selected to have a rating no higher than the ampacity of the conductors it protects, unless specific exceptions apply. The National Electrical Code provides rules for selecting the appropriate overcurrent protection device based on the conductor ampacity and the type of load served. Furthermore, the grounding and bonding requirements outlined in Article 250 of the National Electrical Code must be strictly followed. Proper grounding and bonding are essential for ensuring electrical safety and minimizing the risk of electric shock. The grounding system provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, reducing the potential for voltage differences and creating a safer environment. It is also important to consider any local amendments or regulations that may supplement or modify the National Electrical Code requirements. Local jurisdictions often have their own specific rules and interpretations of the National Electrical Code, and it is crucial to comply with these requirements. Consulting with a qualified electrical inspector or engineer is recommended to ensure that the electrical installation meets all applicable codes and standards. In summary, when a mobile home is used as a construction office, the ampacity adjustment provisions of Section 310.15.6 of the National Electrical Code typically do not apply. Instead, standard ampacity calculation method should be followed, taking into account the total connected load, demand factors, correction factors, overcurrent protection requirements, and grounding and bonding requirements. Compliance with all applicable codes and standards is essential for ensuring a safe and reliable electrical installation. The specific steps to determine the correct conductor size for a mobile home used as a construction office are: firstly, determine the total connected load. This involves identifying all electrical equipment that will be used in the construction office, such as lighting, computers, printers, HVAC systems, and any other appliances. For each piece of equipment, note its rated voltage and current or wattage. Secondly, calculate the total current. For resistive loads like lighting and heating, the current can be calculated by dividing the wattage by the voltage. For example, a 100-watt light bulb operating at 120 volts draws approximately 0.83 amps. For inductive loads like motors, the current can be found in the equipment's nameplate. Sum up the current for all the equipment to find the total connected current. Thirdly, apply demand factors. Article 220 of the National Electrical Code allows for demand factors to be applied to the total connected load, recognizing that not all equipment will operate simultaneously at its maximum rated capacity. The demand factors vary depending on the type of occupancy and the specific loads involved. For a construction office, consult Article 220 to determine the appropriate demand factors for lighting, receptacles, and other equipment. Multiply the connected load by the applicable demand factors to obtain the demand load. Fourthly, calculate the conductor ampacity. The conductor ampacity is the maximum current that a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code provides tables that list the ampacity of different conductor sizes based on their insulation type and installation method. The conductor ampacity must be equal to or greater than the demand load calculated in the previous step. Fifthly, apply correction factors. Correction factors are applied to the conductor ampacity to account for ambient temperature and the number of current carrying conductors in a raceway or cable. High ambient temperatures reduce the ampacity of conductors, while multiple current carrying conductors in close proximity can lead to heat buildup and require further dirting. The National Electrical Code provides tables that list correction factors for different ambient temperatures and numbers of current carrying conductors. Multiply the conductor ampacity by the applicable correction factors to obtain the adjusted ampacity. Sixthly, select the conductor size. Based on the adjusted ampacity, select the appropriate conductor size from the National Electrical Code ampacity tables. Ensure that the selected conductor size has an ampacity equal to or greater than the adjusted ampacity. Seventhly, determine the overcurrent protection. Overcurrent protection devices, such as circuit breakers or fuses, protect the conductors from overload and short-circuit conditions. The overcurrent protection device should be selected to have a rating no higher than the ampacity of the conductors it protects, unless specific exceptions apply. The National Electrical Code provides rules for selecting the appropriate overcurrent protection device based on the conductor ampacity and the type of load served. Eighthly, consider voltage drop. Voltage drop is a decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Calculate the voltage drop for the selected conductor size and ensure that it is within the recommended limits. Ninthly, ensure proper grounding and bonding. Grounding and bonding are essential for electrical safety and minimizing the risk of electric shock. The grounding system provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, reducing the potential for voltage differences and creating a safer environment. Follow the requirements of Article 250 of the National Electrical Code for grounding and bonding. Tenthly, comply with local codes and regulations. Local jurisdictions often have their own specific rules and interpretations of the National Electrical Code, and it is crucial to comply with these requirements. Consult with a qualified electrical inspector or engineer to ensure that the electrical installation meets all applicable codes and standards. By following these steps, one can accurately determine the correct conductor size for a mobile home used as a construction office, ensuring a safe and reliable electrical installation that complies with all applicable codes and standards.